In the previous lesson, we introduced Young's modulus and several important material properties. In this lesson, we will examine a simple beam test that engineers use to evaluate materials. By applying a known load and measuring the resulting deflection, we can calculate stiffness and estimate Young's modulus. These measurements allow us to compare different materials and better understand how they behave under load. Before testing a beam, we must define its geometry. For a rectangular beam, the important dimensions are the width, height, and length. These dimensions influence how much the beam bends under load. Even if two beams are made from the same material, changing one of these dimensions can significantly change the stiffness and overall performance of the beam. One of the most important geometric properties of a beam is its area moment of inertia. For a rectangular cross-section, the area moment of inertia is equal to B times H, cubed divided by 12. Notice that the height appears as a cube. This means that increasing the beam height can dramatically increase stiffness and reduce deflection. Our beam test is straightforward. The beam rests on two supports separated by a known distance called the span. A load is applied at the center of the beam, causing it to bend downward. By measuring the resulting deflection, we can determine how stiff the beam is and estimate important material properties. Deflection is the change of position caused by the applied load. First, we measure the unloaded position of the beam. Next, we apply a known load and measure the new position. The difference between these two measurements is the beam's deflection. Accurate deflection measurements are essential to obtaining meaningful experimental results. Stiffness is a measure of a beam's resistance to bending. It is calculated by dividing the applied load by the measured deflection. A stiffer beam bends less under the same load. Stiffness depends on both the material and the geometry of the beam. Engineers use stiffness calculations to predict how structures will perform in service. Once the load, span, geometry, and deflection are known, Young's modulus can be calculated using beam theory. Before proceeding, it is important to note that the symbol I represents the area moment of inertia of the beam cross-section. It depends only on the geometry and has units of inches to the fourth power. This should not be confused with the mass moment of inertia used in rotational dynamics. Young's modulus is a material property, while the area moment of inertia is a geometric property. Let's consider a practical example. We have a beam with a 22-inch span and a known center load of 5 pounds. After measuring a center deflection of approximately 0.274 inches, we can substitute the values into the beam equation. The resulting Young modulus is approximately 1.56 million pounds per square inch, which is typical for poplar wood. Different materials respond differently to loading. In the example, all three beams have the same dimensions and are subjected to the same load. Because steel has a higher Young's modulus, it experiences the least deflection. Aluminum is intermediate, while wood shows the greatest deflection. This demonstrates how materials selection affects stiffness and structural performance. One of the most important lessons in beam design is that geometry matters. The area moment of inertia depends on the cube of the beam height. As a result, doubling the height increases the bending stiffness by a factor of 8, assuming the material and the width remains unchanged. This is why I-beams, box beams, and other tall structural shapes are so efficient. Engineers often improve stiffness by changing geometry rather than adding more material. In this lesson, we examined how rectangular beams can be tested using a simple experimental setup. By measuring load and deflection, we can calculate stiffness and estimate Young's modulus. We also saw how geometry influences performance, particularly the strong effect of beam height. These concepts form the foundation of many engineering material tests and help us evaluate and compare materials in future experiments. Thank you for watching.